just go ahead and introduce Xiaodan Liang. And it's my pleasure to introduce Dr. Xiaodan Liang. And she is currently an associate professor at the Sun Yat-sen University. And she was also a project scientist at the Carnegie Mellon University, working with Professor Eric Xin. She focuses on interpretable and cognitive intelligence and its application on large-scale visual recognition, automatic machine learning, and cross-modality dialogue system. She has published over 80 cutting-edge papers, which have appeared in the most prestigious journals and conferences in the field of AI, such as Europe's ICML, CVPR, ICCOE. Her Google citation count already exceeds 10,000. She also served as area chairs in many of the major machine learning conferences, also tutorial chair in CVPR 2021. She has also been awarded the ASEAN China and CCF Best Doctoral Thesis Award, the Alibaba Damo Academy Young Fellow Award, and which only give to the top 10, under 35 in China, and the ACL 2019 Best Demo Paper nomination. She was also named one of the Young Innovator 30 under 30 by Forbes China, and she has been working with her collaborators and published the largest human parsing data set to advance the research on human understanding, and successfully organized the workshop about and challenges about this in CVPR 2017, 18, 19, and 2020. She has also organized the relevant ICML and iClear workshop on this. Her current research focus is on self-supervised and lifelong learning techniques for large-scale task-driven visual understanding. Today, she is going to talk about when self-supervised learning meets reasoning. Let's welcome Dr. Xiaodan Liang. And without further ado, I would just give the floor to Xiaodan. Okay.
Okay. Thanks, Professor Song. Okay, so hello everyone. I'm Xiaodan Liang from Sun Yat-sen University in China. It's my great honor to give a talk in a seminar on MBZUAI University. Today, my talk mainly focuses on the recent researches on bridging self-supervised learning and reasoning. Okay, as we all know that self-supervised learning as a form of unsupervised learning aims to exposit data itself as a supervision. For example, in NLP field, BERT achieves the steroid performance by masking out one token and learning to predict it. On the other hand, in the computer vision field, click-like model utilize the large-scale and label data and adopt the cross-model contrastive learning for semantic alignment. There are numerous self-supervised learning methods are approaching the steroid performance in supervised learning for various representation learning tasks. For example, for image classification, cross-model retrieval, and natural language generation. However, in real-world applications, besides the basic classification detection, we must handle the human-robot interaction tasks. It requires a complex reasoning in high-level tasks. For example, in smart education, automatic mathematical problem solving is very crucial for robot tutorial and required to perform symbolic knowledge integration and mining. And the companion robot must be able to deal with the multimodal question answering and dialogue systems. And in the autonomous driving system, decision-making and perception in complex scenarios also need multi-hop reasoning and uncertainty prediction. So existing works only use very tedious manual design, so it largely limits the generation capability. So I mainly explore how to automatically character paragram and with the help of self-supervised learning. So today I introduce from 3 parts. First, I introduce our recent work on self-supervised reasoning on solving the mathematical problems. And secondly, I show our research on searching the thin transformer architecture in a self-supervised manner. Finally, I present the newly built self-supervised learning benchmarks in autonomous driving. Okay, so first of all, automatic math word problem solving has attracted increasing attentions as a long-standing AI benchmarks. For example, math word problem solving, serial proving, and geometric problem solving. And if we can build such a system, so it can serve as a very useful education system tool for students. And it can also enhance your education convenience and your fairness of education resource location. So here I present our recent 3 attempts in geometric problems and math word problems. For geometric problems, we designed 2 kinds of different techniques. One is to use a formal language and symbolic reasoning very explicitly. Another is to design self-supervised learning diagrams and test the self-supervised learning diagram and test the representation learning method. Yeah. And in the math word problems, we designed a different self-supervised learning auxiliary reasoning tasks to improve their performance. So what is a geometric problems? A typical example of geometric problems is shown in this figure. So you can say that its input consists of the problem diagram, program test in natural language, and it requires to output your solution to select the right one from multiple choice answer. So for solving the problem, we need to pass geometric information both in your diagram and test, and combine the test and diagram information, and then utilize the theorem knowledge, and finally we can conduct a multi-model numerical reasoning. Several data sets for geometric problems have been released in recent years. They include GeoShader, GOS, and GOS dataset. However, the dataset are relatively very small in scale and contain very limited program types. For example, there are only 102 shaded area programs in GeoShader and 186 programs in GOS. So while GOS++ and GOS OS contain more data, over 1,000, they have not been published. They have not been public yet. So due to the sparsity of proper data, your task has not been very well studied. And early work was attempted by EMRP 2050. They use computer vision and natural language processing techniques to solve geometric problems. In this work, the system forms both diagram parser and text parser into literal in formal language. And this generated literal further composed of a set of constraints. For problem solving, it formalizes the task as an optimization problem to say which choice can satisfy the other constraint. This work is a pioneer attempts to solve the geometric problems in an automatic way. However, the system does not perform explicit reasoning with knowledge, and it simplifies the task into an optimization problem. So it has no explicit reasoning process, and it fails to use theorem knowledge. So in contrast, our work want to implement explicit symbolic reasoning with the help of theorem knowledge to infer the answer in an interpretable way. So thus we propose a novel geometry problem solver. This is an interpretable approach with the help of formal language and symbolic reasoning. So in this work, we first constructed a new large-scale benchmark named Geometry 30,000 to assess your algorithm performance or geometric problem solving. The geometric 3,000 data set consists of over 3,000 and 2 multiple choice problems. The data set is very challenging because it covers diverse geometric shapes and problem goals. In contrast to existing works, we also annotate each problem test and diagram with unified structure descriptions in formal language. So in this paper, further present an interpretable geometric problem solver, InterGPS. The InterGPS developed an automatic parser that translates your problem text while template rules and passes diagrams by a neural object detector into formal language. In contrast to implicit parameter learning, InterGPS formulates the geometry solving task as problem goal searching, and incorporates theorem knowledge as conditional rules to perform symbolic reasoning step by step. So it demonstrates an explainable way to tackle this task. And also we designed a theorem predictor to infer the possible theorem application sequence for efficient and reasonable searching paths. So in general, a geometric problem P can be defined as total TDC, in which T is a input test and D is a diagram image and C is a multiple choice. So in our project, we want to implement extended reasoning for problem solving. So we formally describe the problem in a geometric domain language, a set or literal composed of predicates and arguments. There are several basic terms used in geometric problem solving. A primitive is a basic geometric element like a point, a line segment, a circle in a diagram. A predicate is a geometric shape, anti-geometric relation, and a function. A literal is an application of one predicate to a set of arguments like variables and constants. So a set or literal makes up the semantic description from the problem text and diagram in a formal language space. And finally, we have theorem to make conclusion from existing literature. We have defined 90 predicates and their corresponding literal templates in a geometric language domain. Here I list some examples. For development, these predicates are can be categorized into six groups: geometric shapes, unary attributes, general attributes, and binary relations, and so on. Our data set, the data is collected from two popular textbooks from online digital libraries. These two textbooks aim at high school students across grades 6 to 12. Groups of well-trained annotators with undergraduate degrees manually collect each problem. With each problem test, a geometric diagram and a 4 candidate choice. In order to evaluate the fine-grained performance of geometric solver, we label each problem data with their corresponding problem goal and geometric shapes. Unlike existing data set that only collect problem, test, and diagram, we further annotate its data with a dense formal language. For example, in these figures, so this formal language description are very helpful to bridge a semantic gap between your test and the real context. And it can also benefit your symbolic problem solver. There are about 6,000 literal for problem test and 27,000 literal for diagram. And we list the most and list the frequent predicates with a frequency greater than 5 in table 4. And it shows the predicates for problem tests are more evenly distributed than those for diagrams. This is mainly because the problem test describes the diverse geometric shapes, attributes, and relations, while diagram only display a basic property of line and arguments. Previous work indicates also indicates a rule-based parser method can be able to obtain a precise passive routes. So we apply this approach with regular expressions to perform test Parser. I think you may ask why we don't use a neural network-based semantic parser. Firstly, the limited data scale of geometric problems has weakened their highly data-driven method. And secondly, the neural semantic parser tend to bring noises in generated results, while the geometric solver with symbolic reasoning are very sensitive to these deviations. So therefore, the semantic parser are not feasible to generate the satisfied literal in our dataset. So for program diagrams, we implement an automatic parser without human intervention to parse the diagram into literal informal language. But the diagram parser first apply half transformation to extract geometric primitives. And then the diagram symbols and test regions are extracted through a straw object detector RetinaNet. And the texture contents are further recognized by an OCR tool. After obtaining the primitive set P and the symbolic set S, we need to grab each symbol with its associated primitive, and we formulate a grading task as optimization problems with constraint of geometric relations. Overall, the inter-GPS takes the relationship set R and the theorem knowledge base KB as an input, and outputs the numerical solutions of the program goal. The relation set R defines the geometric attributes and relations in a given problem, and is initialized by literal formula test and diagram pass. The theorem set KB is represented as a set of theorem, and where each theorem KI is written as a conditional rule. So for the third step, if your premise P of KI matches the current relation set, so the relation set is updated according to your conclusion. After the application of several theorems, so equations between the known value and the unknown problem goal can be established, and the G can be solved after solving all these questions. So as an intellectual task, it's necessary to know the home performance of geometric problem. So we put the test data or the data set in the crowdsourcing platform, MT, and each eligible annotator must have obtained a high school or higher degree, and is asked to answer 10 problems in 25 minutes. And to ensure annotator to use the best of their abilities, they are further asked to spend at least 7 minutes on their problem test and 10 minutes on each problem. So we also ask dozens of graduates, major in science and engineer to answer the questions to evaluate your human expert performance. And this table has shown some results. So compared to the random guess, so human can achieve an overall accuracy of 56. And the human expert can achieve a very good performance over 90%. So we also implemented several deep neural network baseline for geometry solver to compare them with our method. By default, this baseline formalize geometric problem solving as a classification problems, and this neural baseline are fed by the test embedding from a sequence encoder and diagram representation from a visual encoder. Apart from the overall accuracy, we also report the results of different problem types. So benefit from the symbolic reasoning with theorem knowledge. Our inter-GPS obtains an overall accuracy of 57%, significantly superior to all the neural baselines. And the inter-GPS even attains a better accuracy compared to normal human beings. And InterGPS with the graduate formal language gains a further improvement of 20%. That means the test parser and the diagram parser are very important. And our symbolic solver also, even our symbolic solver achieves a favorable performance, but it also requires, it might fail in some very difficult cases. This figure has shown some examples. For example, diagram parser tends to fail if there are very ambiguous annotations or multiple primitives in your diagrams. It's very difficult for a text parser to handle the nested expressions, and symbolic reasoning is still not capable of solving problems that require very complex theorems. So here we can see the formal language and the reasoning pipeline is an extremely complex system, and it's a highly engineered system. So we also explore if there are existing other very easy and very easy to implement system. So here we explore another directions to solve geometric problems. So instead of explicit parser test and diagrams, we propose an self-supervised diagram and test the representation learning. So it's very simple and easy to understand. So because we use a different data set with the previous work is a totally English data set, and GeoQA is a Chinese data set. It's collected from Chinese middle school exams, and the Human expert is about 92%. It provides abundant annotations, for example, problem type, knowledge point, problem solving explanations. And we also provide some programs for helping your neural network model to perform explainable numerical reasoning. Because we do not expect the neural networks with only classification model can work well. So our model must output your program step by step. And the overall architecture of our neural geometric solver is shown in the figure. The problem text and diagram is encoded separately, while a text encoder and diagram encoder, and then fed into a joint reasoning module together to obtain the multimodal fusion of text and diagram features. An encoder utilizes the fused multimodal features to generate interpretable programs. And so here we propose 3 accelerated tasks to enhance the feature representation learning and facilitate multimodal reasoning. So here are our 3 self-supervised learning tasks. The first one is to self-supervise the diagram pre-training. So in order to obtain a high quality diagram feature, it's included jigsaw location prediction to predict correct relative locations of static blocks. And geometric elements prediction is to predict geometric elements appearing in your diagrams. And the third one is a knowledge point prediction. So to enhance the problem's overall representation by predicting your knowledge point used for each problem. We also compare our accelerator model with a test-only baseline and your baseline without using programs, and a list of cross-model baseline. Your supervised accelerator task can significantly help improve the performance. And our designed interpretable programs are quite effective, and you can see the multimodality by fusion the text and diagram is also very necessary. These are some typical cases. So no results means the answer executed by the program is not in the option. That means our generated program is not very good. And the wrong answer represents getting a wrong option. And the baseline is a SEG2 purple plus diagram model. And the left NGS accelerator successfully predicts your knowledge of your theorem through the accelerator task and get your answer. And for a case on the right, your problem is quite hard because the current model cannot solve it. So here also some progress in some progress in math word problem solving. The math problems differ from your geometric problems. It given a story and a question. The model must generate an equation, not a choice, not choose one answer, and give the right answer. So previous pipelines involves from the rule-based design to statistical learning and to deep learning. But current solvers fail to instead incorporate the essence of math symbolic contrast, and it can also include some common sense constant and formulation regularizations. So our model contains three parts. The first part is a program reader. So it's a natural language program, natural language understanding module. And the second one is a programmer. And the programmer to try to decode the equation into an equation tree. And the third one is the executor. Executor is to obtain the final answer by executing this equation tree. And we have designed four different accelerated tasks. And the first one is a common sense constant prediction. Because the common sense constant prediction is to predict which prior common sense knowledge is required. And it can significantly help reduce the search space to solve math word problems. For example, how many legs does a chicken or rabbit have? So it's common sense constant. So we must incorporate such common sense into a natural language understanding. And the second and third one is a number prediction. Is to identify your quantity of number in a program and their corresponding locations in your program test. And the third one is duality exploration. Duality exploration is to enhance the understanding ability of our solver by exploring the quasi-duality between the symbolic graded equation generation and the program's part-to-speech generation. And we can say during your inference, we only need their backbone, a program reader, programmer, and the executor, and also we need their common sense constant prediction to predict common sense knowledge and its number. These are some examples just to show the four accelerated tasks effectively to improve the overall performance. We can say there are different accelerated tasks will help in generating the right equation tree and give the right answer. The above all is my attempts in solving reasoning tasks while self-supervised learning. Here I continue to introduce how the self-supervised learning can be beneficial for exploring scene and transformer architecture. Because as we all know that recent breakthrough has highlighted a journey to explore a hybrid architecture consisting of diversified building blocks, for example, scene and transformers. The figure on the left is a paper from the MIT. It indicates a newly proposed where transformer has reached a comparable performance with a top performing scene, such as the efficient net. And the figure on the right is from paper BOTnet. BOTnet is BOTnet shows us the human design hybrid scene and transformer architecture can outperform both pure scene and pure transformer models. However, manually finding well-optimized hybrid architecture can be very challenging, as on the right side. So the authors of BioTNet have tried 4 different configurations of say 5 stages to study your best design. Just manual scheme is inferior when trying to apply this hybrid architecture to other stages. Because there is substantial blowing of your possible choice. So neural architecture search is a popular approach to reduce the human effort in network architecture design. However, whether NAS can efficiently and effectively handle such diversified search space with disparate candidates is still an open problem. So we accordingly propose the Hydra search space to study the problem. So currently, NAS methods are suffering a dilemma. So multiple trial NAS methods usually take several GPU days to get your architecture rating, while the weight sharing NAS algorithms suffer from the inaccurate architecture rating caused by the large weight sharing space. As only in your figure A, so large search space with layer level granularity has been identified as a main culprit of incorporate in accurate architecture rating in weight sharing NAS method. And in figure B, so the blockwise NAS has reduced the search space by factorizing into blocks and use a pre-trained teacher model to provide a blockwise supervision. However, these results are highly correlated with the teacher architecture. So when training with a teacher with blue nodes, candidate architecture with more blue nodes will tend to get higher ranks in this method. This very limits its application on diversified search space with disparate candidates, such as SAN and transformer blocks. So as shown in figure C, so we accordingly propose a blockwise subwise NAS method aiming to effectively reduce the weight sharing space without introducing biased supervision. So first of all, we factorize the supernet into blocks and train its block or with self-supervised learning. So we replace our teacher model with an EMN supernet, which is potential moving average of the supernet itself. So given your different view of your input, your online supernet is optimized by minimizing the distance between your outputs of two semi-supervised supernets, and this forms the bootstrapping scheme. However, when naively adopting your bootstrapping, so each subnetwork learns from the moving average of itself without a common objective. So the weights shared with different subnetworks will suffer from the convergence hardship. So to address this problem, we propose an unsupervised supernet training scheme named as the ensemble bootstrapping. Its core idea is to use the probability ensemble of the output of EMA supernet as a common target of different online subnetworks. Overall, each training iteration is finished in 3 steps. The first step is that the subnets and the input views are assembled. And secondly, we calculate the outputs of semi-supernets and calculate the ensemble outputs of EMA supernet. And we can update the online supernet by minimizing the I2 distance between the online outputs and the ensemble targets. And thirdly, we can update the EMA supernet. After the supernet training, candidate architecture are rated and searched based on the shared supernet weights. And to form an unsupervised NAS method, we need an unsupervised evaluation metric as an architecture rating metric. However, the training loss is not superable. The training loss is not superable here because there is randomness in sample paths and views. So also previous self-supervised method also use a supervised evaluation metric. So we propose an unsupervised evaluation metric here. So based on our training loss, we first fix the randomness sample views for each subnet, and to ensure the fairness, and then use a probability sample over our architecture as an evaluation target. Thanks to our blockwise weight sharing space, the traversal search is affordable. So we evaluate all the blockwise architecture and rate its candidate architecture by the sum of evaluation loss of its blocks. Here I introduce our proposed hybrid scene transformer search space. So we first use a BOT-net blocks and ZNet blocks as a transformer. As a transformer and the scene candidates, and however, the BOT blocks are very slower than the ZNet blocks and can lead unfair competition. So we accordingly reduce its computation by replacing the relative proportion encoding module in BOT blocks with implicit proportion encoding module. Beyond the building blocks, scene and transformer differ considerably in terms of its macro architecture. Scene usually process images in stages with various spatial size, while transformer typically do not change the number of chip patches and retain their same scale at each layer. So as shown in your figure, to cover both the scene and the transformers, we propose a fabric-like search space with flexible downstreaming operations. We first evaluate our method on the proposed search space. First, the model in our high-chart search space noted as a purple, and they outperform their reported prototypes, the first block in the table, and proving the advantages of our search space design. And secondly, our search model, BossNet T, outperforms other manual and search steroid models such as EfficientNet and BOT-net. And thirdly, the BossNet T can also outperform manual select models and other select models in high trust space, proving the superiority of our NAS method over manual design and other NAS approach. Here is a correlation of architecture search by BossNet and DN. DN is a supervised blockwise NAS method. So as in the figure, so DNT clearly prefers the conclusion as it contains 30 Z conclusion blocks and only 3 Z attention blocks. Z attention block is the transformer blocks. And by contrast, our BossNet T0 has similar numbers of conclusions and attentions, and eventually achieves a higher accuracy. So we refer this to Formula 1, that is candidate preference and attribute to its architecture bias from the teacher supervision. Without using your teacher supervision, our model can successfully avoid the bias while self-supervised learning. We also evaluate our method on the MB search space to compare with more NAS algorithm. First of all, our search BossNet M has outperforms the other NAS models. And secondly, in terms of architecture ranking accuracy, our method largely performs the SPOS and DARTS to other base sharing NAS algorithms. And certainly their architecture rating accuracy has dropped considerably when changing its teacher model. So our model can successfully avoid such teacher preference. And we also evaluate our method on the NASDAQ and the CIFA data set, as in shown in your table. So our algorithm consistently outperforms our other NASDAQ algorithm, and the figure visualizes the correlation between their architecture rating and their real accuracy. Compared with the method CE, so our method can predict your architecture rating more accurately. So self-supervised learning is known as a very popular research directions, especially in diverse computer vision tasks such as object detection and object segmentation, and also the natural language processing. However, it takes a very fair and large-scale benchmark to evaluate your diverse self-supervised learning method, because our current self-supervised learning method is only evaluate your supervised data. So we remove the labels and we retrain your model and we evaluate them. So in autonomous driving, so existing works rely on tedious annotations or all scenarios by deploying in every city and street. And so for SQL safety, so the system need to consider how to handle your long-tail events and the corner cases. And the corner cases, and you're in the unseen domains. So the data efficient methods such as semi-supervised learning, self-supervised learning, and continual learning can assist the training in a large amount of unlabeled data, and which has brought them down to solve your problem. So aiming at facilitating a real-world, ever-evolving, and scalable autonomous driving system. So we present a large-scale benchmark for standardized evaluation of different self-supervised learning and semi-supervised learning approaches by learning from raw data, and which is our first and the largest benchmark to date. And our SODA 10 media contains 10 over 10 million unlabeled data, and 20,000 images labeled with 6 representative object categories. To improve diversity, the images are collected every 10 seconds per frame with 32 different cities under different weather condition, period, and location scenes. And we also provide extensive experiments and deep analysis of existing supervised SRS detection model and popular self-supervised and semi-supervised approach, and some insight of how to develop a future model. For example, we provide MoCo, Sinclair, SWAV, and DASCL, and some video self-supervised learning result to build your benchmark. And we also introduced our one data set for 3D object detection in autonomous driving research. The one data set consists of 1 million LiDAR scenes and 7 million corresponding camera images. The data is collected from 144 driving hours, which is 20 times longer than the largest 3D autonomous driving available, such as the Google Waymo dataset. And it's collected across a range of different areas, period, and weather conditions. So each scene is captured via high quality LiDAR sensor and transformed to a dense 3D point cloud with 70,000 points per scene in average. And for each scene, there are seven cameras capture high resolution images that cover 360 fields of view. And to facilitate our future research on exploring your unlabeled data for 3D detection, we additionally provide a benchmark in which we produce and evaluate the variety of supervised and semi-supervised methods on one data set. We conduct extensive analysis on this method and provide valuable observations on their performance relative to the scale of used data. And based on these two data sets, we host the SCCV 27 and 21 workshop and challenge on supervised learning for next generation industry level autonomous driving. And it includes 3 tracks on supervised learning for 2D detection, 3D detection, and continual learning. And we also award $60,000 for top performing teams. And so let me conclude this talk. Our ultimate goal in our lab is to build a self-involving cognitive AI platform. To build such a platform, we must accomplish 3 levels of learning problems. So the first one is the interpretable learning system. We need to solve some very high-level multi-modal question answering task. And the geometry problems and the math word problems are only 2 examples. And the second one is automatic model design. So we need to automatically design their architectures, design their data annotation schemes, and then how to expand compactor networks. And the final is the continual learning by exploring your unlabeled data, because we need to make the system evolving over times and with increased data. So we need to conduct some self-training, supervised learning, and so on. So that's all for my talk. Thanks all for your listening.
Thank you very much for the talk. It's very nice work. Actually, I have a few questions about the first part. I'm particularly interested in that part, align very well with the research I am doing now. And I believe many other faculty also will find that the other part, transformer CNN architecture, and also for the self-driving car data set you were describing. And they are all very interesting to the faculty here. For the first part, essentially there you have some low-level feature detector, for instance, corner and line detector. And then on top of it, you have this reasoning engine. So I wonder what kind of reasoning engine are you using for, solving those geometric questions. You are using existing engine or actually build your own reasoning engine for it. The second related question is, have you considered pushing gradients through these reasoning engine? For instance, if my low-level detectors are not just very simple feature extractor, but some deep learning models, is there a way to train these feature detector end-to-end with top reasoning engines? Right.
Okay. Thanks for your question. So for your first question, first question, we design our reasoning engine because we need to use a different terminology, because at each step we need a different terminology for the reasoning. So we write the reasoning agent by ourselves, but the reasoning agent cannot be propagator gradients, because the test parser and the diagram parser are separate 2 parts, and we can train it in an end-to-end way, because the test parser and the diagram parser are fine-tuning very carefully. So it also approaching for example 90% accuracy. So it's very hard to propagate your features from your reasoning model. So we design your 3 parts separately.
I see. So actually in your slides, you also mentioned about there may be some inaccurate parser, right?
Yes.
And, yeah, I just wonder how would you improve those? And yeah, so you're going to get more labels, or what's the big problem?
So we have consistent size problems, but we didn't find the right solution, because the text parser and the diagram parser is a very engineer part. And engineer part, and we can output the confidence for each task for a formal language. And we have the probability of each formal language, and we can do some Bayesian inference or reinforcement learning inference, but we cannot change back the results of text parser and diagram parser, because the diagram parser uses object detector and OCR, and the text parser is a role-based parser. So I think we cannot be able to change it.
I see. Yeah. So in general, the task is very interesting. I think it touches, the more intelligent, like AI part, general AI part, because suppose the general AI will contain both perception part and also the reasoning part. So have you considered, for instance, extending your technique to handle some of these, for instance, visual question answer with a knowledge graph, or maybe numerical reasoning with the text, these type of tasks as well, right?
I think we can borrow some ideas from the different fields. I think the visual language question answering is quite similar with geometric problem solving, but geometric problem solving needs theorem prediction and knowledge integration. I think it's quite complex.
Okay, right. Great. Thank you. Any other question from the audience? So one question is related to this self-drawing card data set you are building, right? So the data set comes as some kind of point cloud data sets, or as image and point cloud, and the data is comes with different modalities.
So it contains the image 3D point cloud and a few other modalities. But we only evaluate only LADA-based method, because LADA-based method is more popular in computer vision. And the cross-modality data set has only very few works.
So I just wonder whether in this data set there's also some reasoning component. For instance, you can imagine there's you can detect objects, and then also you might also do some tracking of the speed of object. Then you can reason about the trajectory of the object and things like this to, for instance, to calculate how you should steer the wheel in order to avoid these objects or drive more safely. I just wonder whether this data set could be useful for those kind of tasks. For instance, is there any labeled, maybe in future, kind of scenarios? For instance, in this scenario, the car should drive that way to avoid the collision. In that scenario, the car is better to navigate the other way around to avoid a collision or something. Or maybe sometimes there's even constraint from the traffic regulation, right? And things like, what do you think? Is this?
I think it's a very interesting question. And our data set, we indeed provide some trajectory information, but we didn't include driving decisions. So part of the data set do not include a drive decision, but I think we can in future provide a small test set, maybe include some driving decisions, and you can perform some reasoning task over this scenario.
Right. That would be very interesting, right?
Yes, it is. And in this year CVPR, so it has a paper to show a unified model to perceive, planning, and prediction. So we can design a very end-to-end system to do our learning task.
You mean the perception and
perception, planning, and prediction in a single network.
So that's your paper, or it's
no? It's not my paper. It's a CPR paper. CPR.
I see. Well, what's the name of the paper? You remember, or some keyword find?
I think the name. I think the name. The paper named as a unified model to perceive, planning, and prediction.
I see. I see. Cool. Perceive. Yeah. So have you considered building maybe general system to handle all these tasks, which contain both perception and reasoning part? And so I can see that now you have done this for this geometric question answering part, right? For instance, someone has done it for self-driving car case to unify perception, planning all this. And maybe someone has done something for the just some understanding from text or numerical reasoning from text alone. But is there a way to build or develop some generic system which is easy to customize to these different tasks and handle all these different applications? Just like something like a PyTorch system, right? But PyTorch is just for
I think it's very interesting.
Nothing beyond that, right?
Yeah.
Okay. Yeah, that will be interesting as well. Yeah. So there will be actually another meeting session for you after this talk. So some faculty will be there as well to ask you more specific questions, and you can also ask questions. For now, we can just wait a minute or two and see whether there's any question from the audience. And okay, it seems that we have all the questions from the general audience. Yeah. Again, thank you very much for the talk, and I really like some of the work and very interesting. Yeah. And
thanks for
after we rest, maybe for 5 to 10 minutes, we can join the faculty meeting session. Yeah.
Okay,
you
sure.
Might encounter more questions. Thank you very much. Okay.
Bye.
Bye. See you then.